What time is it now? I think we can, Jeff, I think we can get going.
Okay.
So let's, okay, so let me start things off. Thanks for everybody joining today. My name is Robert Picinic. We're at SolidCAD. I'll be joined today with Jeff Fritsch from Autodesk. He'll be showing us a little bit about CAMplete and what benefits does it give you in the CNC world. So let's put on the next slide for a second here. Okay, so I just wanted to say that we have a couple things that we want to do. We're going to cover a few topics today about CAMplete TruePath and what really what this tool can do for you with your CNC equipment, specifically around some of your more complex equipment that you might have today. We're also going to show, Jeff's going to be able to show us a little short demo. Let's go to the next slide. And I just want to make sure that everybody understands that you can post your questions anytime. I'll try to monitor them. And if we can break into a little bit of the flow today, we'll answer them on the fly, or we'll have plenty of time at the end to answer all the rest of the questions if we haven't already answered them as we go along. So to that ado, please introduce yourself, Jeff.
All right. Well, thank you, Robert, for having me this afternoon, and thank you again to everybody who is attending this afternoon. So as Robert was saying, we'll of course cover a few things regarding the software. Myself personally, I'm a French citizen, mechanical engineer from there. Came to Canada about 17 years ago and started working with a few different CAM software, including EdgeCAM, MasterCAM, developing post-processors, supporting customers, and eventually moved to the simulation side of things, and of course continued to build onto that post-processing, I guess, experienced. And over the 10 years that I've been with CAMplete, we've obviously added a number of machine partners, which I'm going to expand on, and different software partners as well. And that's really what helps really complete the entire solution or the whole chain of the manufacturing process. So we'll of course dive into those aspects of things. And last year, CAMplete was acquired by Autodesk. So now we have the privilege of working and being part of a much bigger structure. And as part of that, the adventure continues, and will hopefully be able to really help you along the way. So just before I maybe dive a little bit more into the specifics of the presentations and really where the software fits into your overall workflow, I think we just wanted to run a quick poll. So really just 4 questions, and just try to get a quick understanding of you know, where you guys would fit yourselves within you know, the different applications available out in the market. If you know, you have an actual need for the verification tools that we would have to offer, especially if you do have a lot of 5-axis equipment, or just a lot of moving pieces, or really wanting to have the assurance of what you're doing is actually going to be supported by the machine. So I'm just going to give it a couple more seconds so that a few more people can answer. I can already see some interesting you know, questions coming up. Do you own 5-axis equipment? I see probably more no's than yes, which is very interesting. So definitely something to dive a little bit more into. So verification software. So most of them no for verification software. Obviously see a lot of PowerMill, Fusion, MasterCAM, of course. So definitely a variety of different platforms used on the programming side of things. Robert, how long did you want to let the
I think
poll run?
if you feel satisfied, we can continue.
Yeah, I think we're about 60%, 7 answers. So at least that gives us a pretty good understanding of you know, where the majority of customers would be. All right. Well, thank you very much for the ones that that participated. So let's dive a little bit into the specifics of really where the software fits into that whole equation. So the best way to really show this is to really I think share a quick video where a picture is worth 1,000 words. So let me share.
Here is we're drilling some coolant holes in this fixture, and we have right over here is where the fixture.
My bad.
There is, and you can see I've already done these holes in the past, but here's what we're doing: 8 of them from this funny lower angle to get all the way up inside of it to allow coolant to drain out. So it's really pushing the limits of what this machine can do. If we look back at the computer file here, I've got this drill which is set up to come in here. I'll just play it real slowly. This is the operation we're going to do, which doesn't look like such a big deal when you're looking at it in Fusion. However, if we post this out to CAMplete, we'll see that the machine simulation of it is, it gets pretty hairy. So let me open this guy up. So here's the machine simulation. And I have different proximity warnings I can set for it. So if I tell it I wanna have it warn me if I get within ½ an inch of anything crashing into anything else. And I go ahead and run this simulation. And so looking in here, we can see there's a lot of stuff going on where it gets really close. We've got the tool holder right here getting very close to the fixture and all this stuff. But the one that's really scary is right here. We have the body of the spindle is getting extremely close to the trunnion table here. We're, you know, really right up there. So I have a ½ an inch proximity warning set right now, and it errored out. So let me. It's gonna sit in there. We use a torque wrench. Just really simple process to lock this in. There we go. Lock the mode in. Right here. Really close.
So I think at that point, all right. So I think at that point, this is really, you know, highlighting exactly where, you know, there may be certain limitations as far as what the CAM system actually lets users see as to how the process is actually going to perform into their machining center. And that's really not that CAMplete is here to replace the CAM system by any means. That's really not the objective. But the objective is really to be able to take what the CAM system does and making sure it's going to work appropriately into the machine tool. So there's definitely a number of situations where, you know, not having the proper code or not having the certainty that the code or the machine will react the way we expect it to the codes, of course, will have a direct impact onto the overall operations of the shop. Whether that is, you know, fairly low impact in terms of having a broken tool, like this one that's just getting snapped, but that can also have a real impact on the overall operation of the shop as a whole if there is a full-on machine crash, which we have seen happen over the years, or there's a number of repeat scrap parts. So as a whole, this has a real financial impact onto the actual operation of the shop. So for those that are not necessarily familiar with the whole post-processing and really how everything kind of works together, one of the easiest analogies that we can do is really to compare that to a printer driver. So we can have a document ready to be printed, click print, but at that point, nobody really thinks about the printer head, how fast the printer head is going to move, how accurately it's going to be positioned related to the page, how much ink is going to come out. All of this process really happens in the background, and we just have the expectation that everything is going to work as we expected and that the printed document matches the original. This is just the world that we're living in. Now, the technology there is obviously there to support that. Would there be, you know, and I'm sure a lot of us have experienced having to chase those printer drivers and not having something appropriate come out. To our world, this is very much the role of the post processor to really convert that toolpath that was generated on the CAM side, to convert that into instructions that the CNC machine tool will be able to run, to understand, to perform the motion appropriately so that we have a proper part coming out. Of course, any type of disruption into that conversion process, if you want, will have, of course, a direct impact onto the results, resulting parts coming out of that process. So really the point there is one way or the other, we really need to make that actual connection between the CAM system where the toolpath is generated and how the machine is going to understand that. And as the machines get more and more advanced, of course, there's more and more complicated or more difficult functions that can be used to, of course, have an impact on the running of the machine. But some of those functions are not necessarily easy. So I'm talking about 3D cut a comp, doing turning into a 5-axis application, some probing application, tool center point control, and dynamic work offset. So there's definitely a mouthful of instructions and engineering that goes with those functions, which are not always, you know, very easy to convert into code. So at that point, this is really where CAMplete, we're going to come into the picture to really help make that connection between the CAM system and the actual code that's going to be produced. And as we're doing this, making sure that really that the code that has been produced will be able to run appropriately into that machine environment. So would there be any issues, as we've seen into the video, that are not necessarily coming from the toolpath in itself, but really all the elements surrounding the toolpath will be interfering. So whether that's at the code level or at the machine level, and of course, ultimately being able to answer really what impact is that going to have onto the part quality, and as a whole, really being able to understand and proactively making sure that we understand the process and how it's going to perform to make the parts that actually need to be made. So if we look at some of those situations, for example, the machine collisions, again, the CAM systems are providing a certain level of simulation, which of course is going to give us a rendering of how the motion of the tool relative to the parts will be into machine environments, but does not necessarily understands or look at how all of those elements can have a detrimental impact onto the machine. So as we can see here, for example, the table going right into, the heads going right into the table is of course not going to be something that can be beneficial to the machine. And same thing with certain positions or situations, tool changing, positioning, retracts. These are all those typical situations where we do see collisions, and that's where the majority of the problems happen, not necessarily during the cutting, but more so during all of those approaches and retracts. So obviously, you know, all kinds of questions that we're asking ourselves, and so these are actual real issues that customers are facing. How do we go about solving this and really understanding where we're fitting into that overall picture? So as part of your overall manufacturing process, as I was saying, we're not here to replace the CAM system, but really enhance what the CAM system does and give the assurance that by building a digital twin, really a digital copy of that process, will have that full understanding and being able to then control and correct any possible issue that would be presented by running that code without any particular attention. So to do this, really to develop that solution, this is something where we've been working directly with some particular machine builders to really cover the entire line of machines and really cover the entire capabilities of that equipment, and making sure that on the software side, we're able to support those equipments in the same way. We'll have that same type of support on the software side to really drive all of those movements for that particular equipment. So in that instance of having multiple CAM systems supported, this is really where now we can become that centralized point where the software will have that ability to run from multiple CAM system inputs. So whether you're running Fusion, PowerMill, FeatureCAM, MasterCAM, Esprit, HyperMill, really, it doesn't matter. It could be even a combination of all of those inputs, and have a centralized common post-processing engine where we'll also have the G-code simulation really built within the post-processor. So it's both elements, the post-processing and the G-code simulation. They're really built one within the other, so that we can not only provide proper code generation for that equipment, of course, having a very detailed simulation to really have a very clear understanding of what is going to happen, and combine both of them so that would there be any issues in terms of how the equipment is going to react, over travels, collisions, all of those elements will of course be detected, and having now the post-processing engine built within the simulation, once those issues are identified, then having the tools in place to be able to correct those issues and make sure that the resolution will be supported on the code side and of course by the equipment, so that by the end we can really make sure that we can answer that question of, are we actually producing a proper part? Is the part that this process is going to make, is that going to be suitable for what my customer actually needs, or to what the ideal part should be? So at that point, it's really being able to combine all of those elements, the post-processing, the simulation, and then wrapping both of them together, fixing those issues, and really being able to look at the process as a whole from really a bird's eye overview. So lots of presentation and talking at this particular moment. So I figured let's dive a little bit more into the specifics, and let's have a quick run at how the software is going to react, and the overall workflow that a user would be experiencing. So here I do have a pretty easy, simple demo parts. So it covers a little bit of everything that a part would typically go through, starting from a piece of stock to a finished product. So of course, a very quick facing operation on top, making sure the block is square, 3-axis roughing, 2 passes, so very heavy engagement into the first pass, a little bit lighter on the second one to give it the shape. And then we start working our way 3+2 around the part. So all of those bosses and pockets, holes, drill tap, all of those good toolpath. And we finish at the end with some full 5-axis on the chamfer. So very different objectives throughout the parts. Heavy 3-axis roughing, drilling, tapping, 3+2 positional, full 5-axis at the end. So we do cover a little bit of everything. As far as the programming side of things, there are really no changes. So you can definitely continue to program the same way you have. There's really nothing that changes there. The first major difference that you're going to see will be at the code generation stage, where now instead of simply post-processing for a particular machine tool, we're going to now transfer the entire project over to Toolpath and do the post-processing there. So that is done typically through in Fusion, the CAMplete apt output that will, of course, grab all of the toolpath, the tool information, so tool holders, all of the different models for part, fixture, stock, where everything is located, start the software from there. So it's a very smooth export where basically just say, yes, transfer all of this information over. I can get notified when everything happens. And then the software Toolpath or CAMplete will now pick it up and we'll start loading all of those elements. So as I was saying, there you go. So toolpath, tools, holders, positioning of the assembly in the machine, part, fixture, stock models. And of course, at that point, really the next question is going to be, what machine are we going to run this particular project on? So at that point, I'm just going to pick a Haas UMC 750. We'll be changing the machine towards the end. So at that point, really, once I have selected the machine, we have all the elements that we know or that we need to really render what that project would look like. So of course, toolpath, fixture, parts, where that's positioned, the machine, the kinematics, how the controller behaves. And at that point, we are now ready to proceed with the actual code generation. So the code generation happens as we're seeing, and the data is being checked for making sure that we actually have all of the supporting information to produce a proper program. So for instance, are we defining a tool? Do we put the tool in the spindle? Do we turn the spindle on? Do we have a plane defined before an arc move? So all those different scenarios will be checked as we're generating the code. And once we do have full-on G-code, at that point, we can literally start running the simulation and really have a very detailed understanding, since the simulation is fully driven by the code, of what the machine will be doing with those particular instructions. If everything is coming out as expected, at that point, we can basically export the G codes and go make the parts with the setup sheet. So very, very smooth transition from one CAM system to CAMplete. So in Fusion, it's done through the post, and every other platform will have a very similar behavior. So I have that same part program here, for example, in PowerMill. So at that point, PowerMill will have a very similar type of plugin that will grab the entire project, the part model, the fixture model, the tools, the stock, start the software from there. And again, very similar experience in, for example, Mastercam, where at that point, same type of approach, where there is a plugin to now export all of those data points. Again, all of the toolpath, tools folder, part location, part stock. So very, very similar workflow where the plugins will really do most of the work. So at that point, we've transitioned from the CAM system onto CAMplete, where now we can start working onto our project. Where now things become a little bit more interesting is really on some of the editing capabilities that the software would have. So let's start, for example, at the overall process level. Right now, we've really built a digital twin of what we had defined in Fusion 360. So this matches one-to-one with what we had in Fusion. Where now things become a little bit more interesting will be, for example, to leverage the fact that I do have PowerMill, I do have Mastercam, where that same part is programmed, where now I can start picking and choosing which toolpath I want out of each platform. So I simply deleted some of the operations that I initially brought in from Fusion, and I'm simply going to now bring in some particular toolpath that I'm bringing in, for example, from PowerMill. So from PowerMill, I'm going to replace some of those operations with some of the drilling and tapping that, for example, is done in PowerMill. So at that point, once this data gets loaded, it simply gets added to my existing process. And now I can see that I'm starting to build a little bit more of an interesting process, because I wanted to be able to do some of those drilling and tapping operations a little bit sooner into my process. And now all of my 5-axis motion is handled into, for example, I'll grab literally the one that was right above it. I was going to go with some Mastercam, but we'll bring some Mastercam elements a little bit later. So at that point, I'm just going to bring in some of those 5-axis toolpath at the very end. So again, add them to my process. And as we're bringing the data in, and as the data gets processed, again, of course, we'll be checking, making sure that the data integrity, that we can make sense of everything that's coming in, is actually there. So in that particular case, we'll see that now we'll have some conflicting information about tooling. So that is one of those issues that comes up very, very often, working with multiple CAM system. Of course, there has to be a match on the tooling side. So in that particular instance, as we're producing the codes, we'll flag some of those issues and say, okay, now this is an instance where we have the same tool number used twice, but the tool geometries associated with each tool are actually drastically different, or different enough that that would have an impact onto the results of the part. So at that point, we now have two different toolpaths where that same issue has been reported, where of course that's going to be a critical error. So now that we're working from multiple CAM systems, I have Fusion, PowerMill, Siemens NX, we'll bring some Mastercam in a couple of minutes. I'm now going to go back to each CAM system, try to find which tool is creating the issue, correct the tool, compare that to my other tooling in my other CAM system, compare both, make it look, it becomes very complicated. Where at that point, we have centralized all of those data points together. We're using the same post processor, and now that we're doing the code generation, now you can have full control over this data and how it gets handled. So for instance, here on the tooling side of things, I'm just going to see that, of course, I have my two tools number 2, and I have my two tools number 3. So at that point, I can, for example, for an easy solution here, I'm just going to simply relabel some of those tools and see that those changes will now be reflected right away into the code. So that's really where now we can really start identifying issues, start addressing them. So of course, at the code level, or the process will be able to reorganize those operations, fix some of those issues that we're noticing here. At the code generation stage, we'll be able to now control what we call the technology that goes around the toolpath. So technology that goes around the toolpath would be, for example, all of those machine neutral functions, whether you're running, in that case, a Haas machine or a Mazak, an Akuma, a DMG, they will all have the same basic machine functions, which would be, for instance, turn the spindle on, which direction, what's the RPM. So that's going to be, in that case, a little bit on the slow side at 500 RPM. If I was to change my tooling numbering like I did earlier on, chances are that would update our offsets as well. So there's my updated offsets. Turns out we forgot the coolant was actually turned off on the very first operation. And now we're really looking at all of those elements as how we're controlling the machine's behavior to the actual intent of the cut. So we understand the positions of the tool are really calculated by the CAM system. And now we're really giving you that level of control back into how all of those elements are coming together, including to the point of really adapting how the machine will actually behave. So at the very beginning, we're really focusing on 3-axis roughing. So at that point, we really want to focus on having lots of horsepower driven through the tool, where the drilling and tapping operation will have a slightly different objective, which again is going to be completely different than the last few operations, which are at that point are full-on 5-axis movements, which will again be completely different. At that point, we'll be looking at very accurate positioning, very defined movements, very smooth, no jerkiness. So completely different approach than the first couple operations, which are really plunging the tool into the material. So that same level of control is going to go down to, for instance, the particular code level. So if we wanted to start working on the code directly, split some of the motion and really make the code your own, you absolutely can. So we can maybe come back to that towards the end if there are any questions. But nonetheless, now that we have really generated all of our codes with all of that technology control and really make the code our own, of course, the next step is really running through the verification process. Can the machine tool actually handle this code the way it was actually produced? So we'll be, of course, there looking for collisions, for over travels, for overcuts. So if we have any type of gouges into the parts, If we wanted to look at particular proximity elements, so between the tool, the fixture, the part, so there's a number of ways we can really start adding particular elements that we want to check. And then of course, full tool change approach, and then at that point verifying that really the machine tool can actually handle the motion the way it was defined in the CAM system. At that point, I'm not going to be watching the entire process. I really want the software to run through every point, check the motion, is everything valid, and let me know if or when there's something either in the code or in the machine's behavior that's not appropriate that we need to look at. So for instance, something to look at here would be an over travel on one of the rotary axes. So I'm just going to continue a couple points. Just where we get it to a pretty interesting situation. So at that point, that over travel, if I hide the machine enclosure, we can clearly see that now that's B-axis over traveled. So looking at the actual machine limits, we can see the machine can only tilt to 35 degrees, but of course, the program calls for something a little bit more. On the other hand, on the other side of the trend, I'm just going to move that up a little bit. We have significantly more travel over here. So really what we want to keep is the intent of the toolpath. So we definitely want to keep this toolpath, the way the tool is going to move into the material, exactly the same, but we just want to be able to pick now the alternative solution and really make those toolpaths, those existing toolpaths, without having to go back to the CAM system. We want to make sure that now these ones are going to be fitted within what the machine is capable of doing. So I'm just going to be looking at which side of the trunnion I'm tilting on, and instead of working on the negative side, I'm just going to be working on the positive side and now have an appropriate solution. So at that point, really the issue was more so driven by how the machine would react to the code. We've identified the issue, corrected the issue on the simulation side, and as we're regenerating now, the simulation is going to have those changes reflected into the code to make sure that now the code is reflecting those changes that we have brought forward into the process. So now that we have that over travel situation sorted out, the next obviously will continue until we reach the next point that now is going to be a full-on collision. So looking at obviously now that interaction between the spindle and the table, we can clearly see that even though the toolpath, the way the tool again is moving around the part is absolutely proper, it definitely does not interfere with the vise whatsoever. It clears the material appropriately. Again, very similar to what we've seen on the very first video. Now, all the elements surrounding the toolpath, so the spindle, the table, how the machine moves, all those elements are now interfering with the actual ability to make this part properly. So looking at those elements, now what options are we going to have available to fix those? So one of those situations could be, for example, to look at the tooling. So extending the tool stick out, how far the tool sticks out of the holder, maybe changing the holder as a whole, would make the spindle sit a little bit higher and hopefully high enough that we could clear, that collision. Another option would be, for example, to look at the fixturing. So if we had a little bit more fixture height, again, once we're tilted on the side, the spindle is sitting further away from the table, again, hopefully far enough that we clear the collision. The third option we could be looking at would be, for example, looking at the table, how the machine is actually being built. In that case, that table is not symmetrical. There is a long side and a short side. So it could just come down to a setup question of really how the part is aligned when it gets clamped onto the table. So if we just rotate the whole thing 90 degrees, at that particular location would now be working on the short side of the table, not the long side, not have that collision altogether. So now, again, even though I am working from 3 different CAM systems, I'm still going to be controlling now how that process on that machine is going to be handled. So looking back again quickly at our tooling, if we go back and pick our tool number 3, now we can start maybe changing that holder for something that may be a little bit longer. So it gives us a little bit more reach. It makes the spindle sits a little bit higher. And by the same token, I can now adjust my my tool stick outs and see how far it actually comes out. So now I'll have those changes reflected into, of course, my spindle positioning. And before I go and continue with the code generation, of course, I see that has improved, but still not quite enough to really clear that collision. So I'll go now add those elements to the fixturing. So looking at the fixturing, when we first started with our Fusion project, on the fixturing side, we only had the vise. Looking at that same project now in Mastercam, we still have our vise, but we also have now a riser underneath. So at that point, that's again one of those elements that I would be able to pick from, for example, from my Mastercam project and add this to what we're currently doing. So now I can go import my geometry directly from my Mastercam project. So in that case, it was just a riser. I'm not really interested in bringing anything else, but just that particular riser in here. So of course, that's going to now give me an updated part position. So considering the riser, of course, that gives me an updated spindle position. And let me see, did it clear it? And I think we're just like shy of really a hair to really clear that that collision. So at that point, we know it's definitely manageable from that point on to really get that that little bit of extra reach. But really, for argument's sake, now, really, the question would have been, what would happen if we just kind of rotated this whole thing 90 degrees? Literally, when we go to clamp it, we'll just rotate it 90 degrees or rotate your whole thing. So at that point, it would have become super clear that we didn't necessarily need to look at the tooling or the fixturing. The fixturing definitely helps in any situation, but at that point, the tooling could have stayed maybe a little bit shorter and a little bit more rigid. But at least now we do have that perspective. We do have those tools to really answer those questions and look at your parts process development and be able to explore different possibilities and avenues as well. So getting very close to the end, I maybe have another 2 or 3 minutes of cool features to share with you guys, and then we'll
yeah. Do you have time to answer one question?
Oh yes, yeah,
sure,
please.
So we got one, well, we got a couple of questions, but we'll answer one at least. Can a customer build their own machine models?
Not from scratch. So the kinematic definition, really how the axes are built one on top of the other, is something that is controlled by CAMplete, by the technical team, simply by how the post processing is done in the software. It's done differently than what the CAM system typically handles. So at that point, the short answer would be no, not from scratch. However, once we have provided a machine and it is, let's say, the same type of kinematics, and at that point, yes, you can definitely make a copy of it and modify it at leisure, but not from scratch. So we can look into the machines and how they're put together, and I can definitely give you some of that insight there for sure. Okay. So let's go add some stock very quickly in there as well. We can really now start to look at exactly what is going on when we're actually making those cuts. So let's whoa, went a little fast there. I wasn't expecting it to go it's fast. So let's keep it running for maybe a couple more seconds, and then we can just stop it and see exactly where that's going to go. So what I'm really doing there, as I'm running the simulation, of course, it's still going to verify all of those collisions and over travel and all of those elements. We can hide some of those. But at that point, it's also going to do, of course, the materials removal. And now all of those data points are really going to be tagged along, and of course I'll show you whether that is a valid movement, if we're going to have any type of over travel or gouges or anything funny that could be happening. Really the objective there will be to tag all of those calculated data points, which are really there to help us build a picture of that process. Really, where's the machine at? Where is it going? How fast does it go there? What is the shortest way? Is that a feed rate that's actually within the range of how fast the machine can move? And what I'm really more interested in here and that I wanted to highlight is really those volume of material removed and volumetric material removal rate. So I know that's a mouthful, but really what that means is now we can really use all those data points to really build that picture of the process and identify any possible issues that would typically be associated with 5-axis machines. So you've seen a lot of C-axis jerkiness when you get very close to the vertical position, one axis that accelerates very fast into a sharp corner, which axis of the trunnion, do you have a lot of reversal? So all of those behaviors will be seen very clearly. But what I wanted to really highlight there with that volumetric material removal rate and basically how much material gets removed, now we can really see the tool engagement into the material. So the first operation, we really don't see a whole lot of interaction. We're just squaring the block out. The second up is really where a lot of the 3-axis roughing comes into play. And then at that point, we can clearly see that a lot, not a lot, but some points, there's 1, 2, maybe 3 points are really high in terms of engagement. And one of them really maxes out. Chances are we can't even break the tool into that particular corner. So at that point, really, if we were to reduce that feed rate at the controller level, that would affect every point in the program. Of course, the very high point would be affected, but the low points would be affected in the same manner. Where really now having that understanding and being able to visualize what is happening in terms of tool engagement, now we can selectively say, okay, those high points will now be reduced at those particular points. Not the entire program, we'll keep every point the same, except those that are really high in terms of engagement. We'll bring them back and check with the rest of the program. And those second passes that now we can see are already very low in terms of engagements, now being able to bring those points and double or possibly even triple that feed rates at that particular second pass, because now we know there is a lot less material and there is that opportunity to drastically increase that feed rate and remove a lot more material in a much shorter period of time. So at that point, that's really where we'll be relying on this information and more so on the optimization side. But at the end of the day, all of those tools are really here to help us answer that question of, did this process actually create a proper part? So let me just do that again. Looks like I missed a step there. So this guy and that guy. There you go. Okay. So at that point, yeah, being able to compare what the code actually has cut with all the changes that we've brought forth, has that actually cut a proper part? So any type of material left over, as we've stopped it very early into the process, will of course be flagged. Any type of gouges will be shown, and really having that overall understanding of what that process will produce on that particular machine tool, and if that's going to work for you. And the last cool feature that I wanted to highlight, and then we'll take some question, is of course, if at that point you don't have that particular machine tool, as the question was, can you build it from scratch? No. However, any other machine that's we're supporting at that point, you can very easily move that onto a machine that may be completely different in terms of kinematics, how the machine moves in controller, and really it comes down to how all of those elements are really all put together. So at that point, you would still have a lot of flexibility to keep all the changes that we have done at the process level and simply have them repeated into a machine that may be completely different. So as a whole, I'm just going to be finishing that up as we're kind of taking some questions. So, Robert, was there anything else that has been surfacing as I was?
Yeah, sure. Sure, while we're at it.
Sure.
So there's a question here. Does CAMplete have an API? And can a lot of this be automated?
Yes, very, very good question. Unfortunately, the short answer is no. There is no API. We've had a few requests over the years, but nothing that has that really has panned out to be anything that's available in the software at that point.
And we have one more question.
All right.
Can you output mirrored NC files?
Oh, very good question. Actually, interestingly enough, I've had that conversation with a customer a number of years ago. Yeah, they were asking about mirroring capabilities. So unfortunately, no. At that point, that's not something that has been implemented in the software. And one of the reasons for that is really the CAM system does a fantastic job at doing that, and they definitely do that extremely well. From a code perspective, really the way we do the post-processing here and the way we handle this, this is really something that would be definitely a fair amount of work for a capability that the CAM system already has and does handle very well. So short answer, no again.
Well, I definitely would agree to use the CAM system to do that anyways, because yeah, as you said, there's a lot more control, and you know, you want to verify the post with CAMplete, not so much having to reconfigure all the different mirror portions and stuff like that. So
exactly,
it's good. I have a while this is going, I have a general question that I had from a customer that couldn't attend today's session, but he did ask me to ask the question.
Okay.
He has a very complex machine, and he's in the woodworking industry. It's a gantry style 5-axis milling machine, but basically they cut wood and they cut complex geometry. So do you guys support those types of machines in that industry?
Actually, again, very, very good question. So yes and no, in the sense that we would support, you know, the overall 5-axis architecture. So even if it's a gantry machine, we definitely have supported customer that do have, you know, router type of machines. So I think actually there's one. There you go. So that would be one. I really don't have any idea what shape it is in. I literally just click the button. So we'll see how it comes in. But yeah, there you go. Actually, funny enough, I think there was one machine that was running at Autodesk. But so that being said, yes, we have supported some of those machines in 5-axis configurations. However, more to your point of specific woodworking, over the years, for sure, we have seen, you know, on the woodworking side, there is definitely a little bit more specifics application. So I'm thinking block drills, saws, tool tables, or alternating tables, and you know, there are some controllers that are really finicky with the type of code they take. So at that point, we're really looking at it as you know. Yes, we can support the 5-axis side of things, but as far as, you know, doing block drills and really woodworking specifics, we wouldn't take that part of. But yes, as a router, 5-axis router, yes, we would be able to do that. Let me just fix the part.
Awesome.
All right, let me just fix this part. Make sure we can run this thing. I've brought it up.
Yeah. Nothing like having a live session with
right?
with something complex.
Exactly.
Well, that being said, I mean, you've already proved that you can put in another. I have a question. How easy is it to change the machine? So you're going to be able. You just brought in all the code.
Oh yes. So
specifically.
exactly. So, you know, just during the presentation, I have literally taken that exact same parts that we had running on the highest UMC 750, put it onto a Grobe horizontal 5-axis with a height. Now it's on the router head. So completely different in terms of how those machines move, behave, are controlled. But the underlying manufacturing process in that case is really something that we own, or the customer owns and controls, and define how, you know, they're running some of their toolpaths from Fusion, from PowerMill, from NX, from Mastercam, from really any combination of those CAM system, and really give them the assurance that it's going to run into that machine. So very quickly now, as we're on the topic of those machines and how all those elements are put together, really there's a setup there that highlights this very, very well, where at that point, really, when we're working with the machine builder, we really try to accommodate every possible scenario that a customer would be encountering. And that's exactly how those machines are being built. So of course, we'll see exactly what the results will be, but really how that machine is configured. So all your different coordinate system, how those axes moves and behaves. So home positions, minimum, maximum feed rates, acceleration, deceleration values. So both linear, rotary axes, all your system variables. And in some instances, depending on the machine controller and how it's configured, we have that ability to go directly on the PLC side of the controller, extract those machine parameters, kinematic tables, really that fine detail of how the machine is actually set up, and use this information to now drive the simulation. And that's really the process of building that digital twin. So if we look at, for example, how a tool change motion or tool change sequence is actually performed, at that point, this is not hard-coded value to say, okay, the spindle needs to retract to Z 400 millimeters. At that point, that really becomes unique to how each machine is implemented and set up and leveled by in that case, the machine builder. And the simulation now becomes interactive with how the machine is actually configured. So at that point, it's not a hard-coded value. It really comes down to a particular machine parameter, 4210.5 at that particular moment. So looking at that parameter, that exact machine that was running that was set up at 430.5 millimeters. So at that point, this is really how we build that digital twin. And that gets coupled now with, for example, that NC format, which is the post-processor that almost in plain English will really lay out very easily how the post-processor works and what the output is. So how do we start a program? How do we start a path? How do we do a tool change? What type of cut do I have? 3+2, 5-axis, 4-axis, and so on. And now in each one of those blocks, we've really taken all of the software engineering craziness out of the equation and replaced that with plain English, almost plain English, actual machine function. So that means we don't like where the comment comes out, drag it and drop it where you want it to come out. You want a new machine function that hasn't been, you know, producing the output you wanted. Let's say we want to add TCPC. We'll add it and tell us how it's controlled. Is it enabled? Is it enabled? And if you really wanted to dive very deep into it and start building macros and really control your process to a much greater extent, and say, for instance, I would want to build tool breakage check macros after every drilling operation or tapping operation. So if your tool, if we're doing, oh, let's see, where's my tooling? So interesting. Oh, there. So if my tool is a drill, then I would put the tool breakage check. If not, then I would put something else. If I'm doing probing and this output comes out. So now we're really having a lot of flexibility that can be part of the process as a whole, that not only now is it going to produce the code the way you want it, but will also verify it that the entire chain of events will actually be working the way you expect it to. So, was there any other questions, I guess, on the...
No more questions at this point. I haven't seen
on
anything.
The panel. All right.
Yep. So I guess, yeah, we're coming down to the last few minutes of the hour. Yep. Thank you very much for your attendance today.
So let's just go back there quickly. I think there was a couple things. So of course, now we've gone through this. So as I was saying, there's obviously a number of machine partners that that we have worked with very closely over the years. But that doesn't mean that this list is limited to a certain extent. Of course, there's all kinds of other machine tools that we're supporting as well. And of course, if you have equipment that may not necessarily be on this list, that doesn't mean it cannot be supported. There's plenty of other machine tools that we have supported for customers over the years, and we'll definitely be happy to do that for you guys. So I think at that point, the next slide is maybe more for you, Robert.
Yeah, thank you. Thanks again, Jeff, for helping out today. It was a pleasure to get you to show off your skill sets, and awesome to see some of the stuff that we can do. As far as the SolidCAD team, I'm part of the advanced manufacturing team. As you can see, we're up highlighted here. We cover all of Canada, but we also have been able to do services and other things that we can do out of the US as well. But more importantly is we're always there to help your team. Our team's there. We have our support system that we have live people you can talk to. So that's an important aspect. You just have to send us an email, but you can call us live. We have also on staff, we have not just a tech and sales, but we also have our own development staff team internally as well to help. Either it's creating posts or machine simulation files, or even, automation in some of our tools. And, not that, this is the topic to, or this was the session to say it, but we did develop our own make productivity tool for PowerMill, which is an awesome tool to look out for. So maybe what you could do is check out some of our other videos on YouTube that we posted, and we'll definitely post this one as well later on. So, again, thank you very much. Sorry about the slide here, but we are covering, we have all of our training facilities all across Canada that when we start to reopen in our offices, let's just say, because we are in a bit of a pandemic as it would be across the globe. So we want to make sure that, people know that we can cover you as well online. It's a very popular thing to do nowadays. So we are doing our training sessions online for now. But when we get to the offices, we'll be glad to invite you guys into our offices. Reach out to us. We do have our support channels, ams.support@solidcad.ca. If you go to the next slide just for a quick second here, or just reach out to me directly, and we can definitely steer you in the right direction for answering any of the questions. As well, follow us on all the socials, and look out for this one on YouTube. It'll be replayed again. Thank you again, Jeff.
All right, you're very welcome. Thank you, guys.
Thank you all. Take care.
Bye-bye.